Hello maths fans. So today's video is going to be all about the fundamental theorem of calculus. This is probably something that, depending on your level of experience, is either a theorem you use all the time without even thinking about it, or else it's something you've never heard of. In both cases that's a bit of a shame because it's a really interesting and really beautiful and really important theorem that has a lot of really useful applications. So I'm going to try and explain it in such a way that everyone can understand and hopefully everyone finds it interesting. So here we go. Okay, so the first question we have to ask is, what is this thing calculus? So calculus is really studying functions. So a function might represent anything. It might be the velocity or position of an object. It might be the price of a particular commodity over time or whatever. And you can draw a graph of that function. So we often call a function f of x. Apologies if this is all very familiar to you, but just to get everybody caught up. And so when we do this area of mathematics called calculus, we do two main different things. Differentiation, where we seek to find out really how fast that function is changing. And here's how we do it. So if the graph looks something like this, we look at a point on the graph and we say we want to know how fast the function is changing there. That's the same as asking how steep is this line. Is it going up a lot? Is it going down a bit like it is here? And the way we do that, so we take this point, we'll call it x, we take another point a little bit further along, like so, and we draw a line between them, and we ask, well, how much does the function change between here and here? So we do that like this. We say, well, what's the function a little bit further along? And what was it at the start? We divide that change by, okay, how much time has gone past, or this small change here. And then we take the limit as that change tends to 0. So that might be a little bit of a confusing thing, but basically you can imagine we take these 2 points and we just look at them getting closer and closer together, and we get closer and closer to seeing just how fast the function is changing there. So that's the first part of calculus. It's all about finding rates of change and slopes of curves. The second thing we seek to do in calculus is this thing called integration, which sounds all super clever. That really is just a fancy word for finding the area under a curve or under this function. So we might be looking between A and B, for example, and we want to know what is the area here. That's a little bit difficult to work out, obviously, because the top there is curved. So the way we do that is we slice it up into lots of rectangles. So we make a lot of rectangles. You can see this isn't going to be an exact area, unfortunately, but there's a solution to that. So we slice up a whole bunch of rectangles that are as near as we can get to being the area. We find the area of all those rectangles. And then again, just like we did before, we take the limit as the size of the rectangles tends to 0. So I'm just going to write that like this. Or the limit as the number of rectangles tends to infinity is the other equivalent of, let's just say, area of the rectangles. Okay, so that's the other thing we can do. And we denote that with this fancy integral symbol. So we said integral of f of x dx. That's that area under the curve. And the differentiation that we found earlier, we have this thing called the derivative, which is f prime of x, which is equal to that. Okay, so that's basically what calculus is all about. We're either finding rates of change and slopes of lines, of curves, or we're finding the area under curves by cutting them up into lots of little rectangles. And the amazing thing about the fundamental theorem of calculus is that it says that there's a really deep and meaningful connection between this process, where we find the rate that something's changing at, and this process, where we find the area under that curve. So the fundamental theorem of calculus says the following. It says that these two processes we've talked about, finding the area underneath the curve and finding the slope or the rate of change of that function, are actually opposites of one another. They're inverse operations. So if you find the gradient or the rate of change of a particular function, and you graph that rate of change, and then you find the area under that graph, you will have back your original function. And that's a pretty amazing thing. Again, anyone that's a student of calculus probably uses this fact all the time. You know that differentiation is the opposite of integration and vice versa. But I don't think it's obvious at all that these two things, this finding the area under a curve and finding the slope of that curve, should be in any way related, let alone related in this really fundamental way that the one operation is actually the opposite of another. I can show you a little sort of proof. I'm going to put it in inverted commas because it's not a proper proof with, absolutely watertight, but it's a little sort of demonstration, if you like, of where this theorem comes from mathematically. And it works like this. So we start by looking at our function, and we define the function a of x to be, let's say, the area under that curve as far as x. So that's that pink area that I've shaded in there. And if we look a little bit further along, perhaps, another point x plus h, you can see that now the green area there, that's the area at x plus h. And if we look at the difference between those two, so we look at the area at x plus h minus the area at x, well, that's basically equal to the area of this bit left here, which is sort of a rectangle. Sort of, close to being that rectangle. It's a rectangle then with this little bit of error here. So we'll say it's a rectangle, and the area of the rectangle is the height here, the function here, times the width, which is h, plus, let's say, a little bit. Not proper mathematical notation, but it'll do for today. You can rearrange this little equation that I've written here to say that, well, actually, let's solve for the function. I'll save you the algebra, and I'll show you that it comes out like this: a of x plus h minus a of x all over h minus a little bit over h. Okay, and then when you take the limit as these 2 points get closer and closer and closer together, so as we make h smaller and smaller and smaller, so we take the limit as h tends to 0. Well, we're going to have the limit as h tends to 0 of this, and the limit as h tends to 0 of this a little bit over h term. And this is where my proof becomes a little bit less rigorous, because you're going to have to trust me that this goes towards 0 as h goes towards 0. That can be proved. I'm not going to do it now, but you can prove that this little correction term, this tiny little bit here, that divided by h actually does, that little correction does tend to 0 as h tends to 0. And so what we're left with is this. And if you remember back from a minute or two ago, that limit as h tends to 0 of function at x plus h minus function at x divided by h, that is the definition of the slope or the rate of change or the derivative of the function. So this is saying that our original function at x is equal to the slope of the area function at x, which is what the fundamental theorem of calculus said, which is that if you differentiate, so you find the slope, and then you integrate, you get back to the same function. So you integrate, that's our a of x, and you differentiate, and you get back to the same function. So what is this good for? I said it had some important applications. Well, this thing is all over physics. In physics, we use a lot of things depend on time. A lot of things change in time. A great example is your position. If you're moving along and you plot a graph of your position against time, maybe I'm moving a bit, I'm moving forwards and then I'm moving backwards, and I plot a graph of my velocity against time. My velocity is, that's another piece of physics notation there, just the rate of change of my position with time. So that's just the derivative of my position with time. You probably know this if you've studied some physics. The derivative of my position, as time goes on, the rate of change of my position, is my velocity. But so the fundamental theorem of calculus then obviously means that my position is in some sense the integral, or the area underneath the curve of my velocity over time. And this is, again, something everyone who studies any physics uses this all the time, every day of their lives probably. Another consequence of this is the fact that, remember, this integral, this area under the curve, we originally worked out by adding up or summing a whole bunch of areas of rectangles, which was the function multiplied by the width. So in this case, that would be the velocity multiplied by the time. What this statement effectively says is that you can, if you know the velocity of an object at all times, but you don't know where it is, but you know where it started, you can work out where it is just by adding up all those little velocities times a whole load of little times. So if you go this way, this way, this way, this way, this way, this way, you can work out where something is. Which again is actually quite an intuitive idea. And obviously super important in physics or in any sort of field where something is changing with time, this ability to work out where it ended up by how it changed through that time. And it all comes back to the fundamental theorem of calculus. So I hope you enjoyed that little tour through the fundamental theorem of calculus. Apologies if it was way too basic for you or went over your head a bit. I'm sort of trying to achieve the impossible of making it accessible to everyone while simultaneously be interesting to everyone. If you liked it, hit subscribe, hit like, tell all your friends about it. Try and make this channel even bigger if we can. I know my grade 10s who persuaded me to do this in the first place will be delighted if we can get to a few hundred subscribers, let's say, a few thousand, a few million, who knows? Let's see where this thing goes. Until next time, goodbye.